All right, today we're going to be talking about the physics of movies. Our group is Sid, Asha, and myself, Tarun. So our three topics for this presentation are mechanics, relativity, and waves.
First, we're going to be covering the good physics in the Marvel Cinematic Universe.
Undying.
In this scene, Thanos uses the Space Infinity Stone to arrest Loki's dagger thrust in midair, and all of the momentum is stopped. According to Noether's theorem, for every symmetry, there's an associated conservation law. This theorem links two major concepts in physics: conservation laws and symmetry. A conservation law states that a particular quantity must remain constant. Symmetries describe changes that can be made without altering how an object looks or acts. And symmetries in physics includes how equations don't change in different places in time or space. With this linkage, Noether states that momentum conservation is due to translation symmetry in space. So, Thanos' use of the Space Stone to command momentum is scientifically accurate and backed by physics. Now, moving on to bad physics of the Marvel Cinematic Universe.
Sure seems different from down here, doesn't it, Scott?
What? Who said that?
In this scene, Ant-Man shrinks to a much smaller size and continues to talk to another person, and they're able to hear him. Since Ant-Man is in this smaller form, his vocal cords will also have shrunk. Using the equation for finding the fundamental frequency, we can see that a much smaller length with constant mass will increase the fundamental frequency. So through physics, we know that nobody should actually be able to hear Ant-Man, since the frequencies he would produce would be out of the range of human perception.
So for our next movie, we're going to be going to Star Wars. So here's some good physics in Star Wars.
Have you now? What? Yahoo! Look out! You're all clear, kid. Now let's blow this thing and go home.
So in that clip, the Resistance destroyed the Death Star using a photon weapon. A photon weapon is a high energy beam of charged subatomic particles, and they destroyed the Death Star by one of three methods, or a combination of all: by disrupting the atomic structure of the center of the Death Star, by overheating the center, and or by electrically neutralizing the center. And so how they create a photon weapon is there's a three-step process. So one, they ionize an atom by removing or adding an extra electron. And then once the atom is ionized, you accelerate the atom to a very high speed. And then you would neutralize the atom, and the change in energy allows the subatomic particles to do damage. So for a similar analogy, you could take a look at a linear particle accelerator. So now for some bad physics in Star Wars.
Strap yourselves in. I'm going to make a jump to light speed.
So for hyperspace travel, there are two different components: the ability to travel at light speed and hyperspace to exist. So because the Millennium Falcon has a mass of non-zero, it can't travel at light speed, which is stated by physical theory. But the Millennium Falcon apparently has an engine that can accelerate to the speed of light, which proves that this part of hyperspace travel is not possible. So if we take a look at the other part of hyperspace travel, there's the actual hyperspace, which is another dimension according to the creators of the Star Wars movies. And how hyperspace works is when a ship wants to travel in hyperspace, they would have to contract the space in front of the ship and expand the space behind the ship. And that's how this is theoretically possible, but based on current physics knowledge, this is not possible, and it's very, very vague as well. And if even possible, they predict it would be like in the next 3 centuries sometime. Yeah.
So now we'll be covering some good physics in Interstellar.
Hello, Rob.
I've waited years.
How many years?
By now it must be.
It's 23 years, 4 months, 8 days.
Doyle?
But I was prepared. I knew the theory. Reality's different.
And Miller?
There's nothing here for us. Why didn't you sleep?
Oh, I had a couple of stretches. I stopped believing you were coming back. Something seemed wrong about dreaming my life away. I learned what I could from the black hole. But I couldn't send anything your father. We've been receiving, but nothing gets out.
Is he alive?
Oh, yeah.
So what happens, for context in this movie, is that the two astronauts actually visit a planet called Miller's Planet in this scene. And what happens because of gravitational time dilation is that an hour that they spent on that planet actually translates to 7 years on Earth. And so they were actually stuck on the planet for about 3 hours, thus, because of which their fellow astronaut in space had to experience actually 23 years of time, even though they only experienced about three hours of time. And that's actually a true thing, gravitational time dilation. Basically, the rate of time changes based on the mass of the object. As you can look at the diagram below there, you can see the Earth, the Sun, and a black hole. Each of these objects have very drastically different masses, and thus the time that each of these experience is different. It's a very simple physics logic, the way you think about it. If you're going from point A to B, it takes about a certain time if you're going at a constant speed. Now, we're assuming the constant speed is the speed of light. And to go from A to B, it takes about a certain amount of time. However, if you're going from C to D at the same constant speed, where the space-time, which is actually curved, as you can see right there, that means that light has to go through a longer distance, thus creating more time for it to go through. And this has actually been proven. You can see the time dilation on our GPS satellites, which are about 12,550 miles away from the Earth's gravitational field, have clocks that run faster. And thus, people operating on Earth have to constantly change these clocks in order to match with the Earth's time. Let's move on to some bad physics in Interstellar.
The backup generator kicked in, so the system's stable. They're all good.
Good. Okay. The navigational hub has been completely destroyed. We don't have enough life support to make it back to Earth, but I think we can scratch our way to Edmund's planet.
Well, what about fuel?
Not enough. But I have a plan. We let Gargantua pull us down close to her horizon. and a powered slingshot around, launching us towards Edmund's planet.
Manually?
That's what I'm here for. I'm gonna take us just inside the critical orbit.
What about the time slippage?
So the bad physics in this scene is that okay, so Gargantua, which is the black hole that they saw in that they show in the scene, it is possible for planets to orbit these orbit black holes in real life, and that is possible. That's one of the theories that black holes can act exactly like suns. However, the issue with black holes is that they do not reflect as much light as you can see in the movie. Black holes actually are strong enough to completely absorb or extract all the light around it, and thus the amount of light that you can see there is not really possible, which is the wrong idea. Secondly, the entire premise of the movie is that there are habitable planets around this black hole called Gargantua. However, that's not truly possible, again, because these because the black hole does not have the capabilities of reflecting a lot of light, which is, as we know, an essential part of life for at least humans on habitable planets. And thus, these planets would actually be frozen and uninhabitable had they existed around this black hole Gargantua. And thus, that's one of the wrong things that Interstellar got, just that the proposal of having habitable planets around these massive black holes and the fact that they can reflect so much light to allow habitation.
All right, so that was our presentation. Good physics in Star Wars, Interstellar, and the Marvel Cinematic Universe. Thank you.